Hey everybody, welcome to the next video lesson. In this video lesson we're going to talk about molar mass. In the last video lesson the number of particles was Avogadro's number, but that's actually not too important to us, but molar mass is.
Let's consider oxygen for a moment. As we know, oxygen is symbol O and its atomic number is 8, which means it has 8 protons in the nucleus. Now this number down here, way back in chapter 1, we talked about being the average atomic mass of all the known isotopes of oxygen. This number is calculated by taking the isotopes of oxygen and calculating a weighted average. Now this number is also important to us because it represents something known as molar mass. Now the difference between them is the average atomic mass is measured in atomic mass units, or AMUs, whereas the molar mass is measured in grams per mole. So if you're talking about a single atom of oxygen, its mass is 15.9994 atomic mass units. But if you're going to take an entire mole of oxygen and measure the mass of that, then its mass is the exact same number as the atomic mass, but in grams per 1 mole. The molar mass represents exactly 1 mole of an atom or molecule. It's how many grams there are in that 1 mole. The atomic mass in grams is the molar mass. Now what molar mass provides for us is another conversion factor in order to do some more dimensional analysis involving now atoms, mass, and number of moles. Now, if we're going to do dimensional analysis with this, it's important to know that this is not a constant value. Now, we can do dimensional analysis with Avogadro's number, and that number is constant. No matter what the substance is, it is equal to 6.02 times 10 to the 23rd particles. But since the mass of substances change depending on what you're looking at, then the molar mass also changes with the substance. So a molar mass is unique depending on the substance. And you can not only have molar masses for just individual atoms, but it also works for molecules. For example, carbon dioxide, a very common molecule that we all know about, is really the sum of carbon and 2 oxygens. So if you want to calculate the molar mass of a molecule, all you need to do is add up the molar masses of the substances that make up that molecule, and you will get the molar mass of that molecule. Now you can see that I've reported the molar masses of carbon and oxygen underneath each one. And what you can do for each of these is actually round them off to 2 past the decimal. Because they are not a significant value, you do not need to worry about rounding rules. Rounding rules do not apply because these are pulled off a periodic table, and numbers off a table don't count as significant values. So round them off at 2 past the decimal and then add them, and you'll get the correct answer. And the molar mass of carbon dioxide is 44.01 grams per mole, which means that there is 44.01 grams for every 1 mole of carbon dioxide. What that means is if I have, say, 2 moles of carbon dioxide, then I have double the mass. It's proportional. 3 moles, triple the mass. 4 moles, quadruple the mass. It's 44.01 grams per 1 mole. So here's an example involving carbon dioxide. How many grams of CO2 are there in 1.05 moles of CO2? So, like every dimensional analysis problem, I begin with the number over 1. So I have 1.50 moles over 1. And I convert by matching moles in the top left and moles in the bottom right. Now, if this was an Avogadro's number question, it would say how many atoms of CO2 are in this many moles. But it doesn't say atoms, it says grams. So I put grams on top. And now I take that molar mass from the problem up above, and it tells me exactly how many grams there are per mole. So I put 44.01 grams over 1 mole. The moles cancel, and my answer here is going to be 66.015 grams. But I want to round that off to 3 significant figures. Now the 1.50 is 3 significant figures, so this is 66.0 grams total of CO2. And a different type of question that I could present to you is one where I give you grams and convert to moles. So if you read this problem, I have grams now. It's important that I know that I'm starting with grams and I'm converting to moles. And so I can set up the problem just like I did before. I take the 20.5 grams of NaCl over 1 and I multiply by a fraction. Grams of NaCl go opposite. This time moles of NaCl go on top. And I'm going to use the molar mass. Now the abbreviation MM here stands for molar mass, so I've given it to you. Now I won't always give it to you. I may ask that you actually pick up your periodic table and add it up yourself. In fact, in these beginning problems, I'll give you the molar mass, but by the end of this chapter, I'll expect that you use your periodic tables to find it all on your own. So you simply say that for every 1 mole, there are 55.85 grams of NaCl, and this time you divide these two numbers to get moles of NaCl. And the correct answer, rounded to 3 significant figures, once again, 3 sig figs right here, the answer is 0.351 moles of NaCl. So now I want to scroll up a little bit here and kind of talk about like the overall situation that's happening with moles and mass and molecules. I'm going to sketch out a little flowchart or a little diagram for you to help you kind of organize your thoughts when it comes to doing these two types of problems, because these are two types of calculations that you'll be expected to do on a quiz coming up here in the near future. If you think of the unit moles being in the middle of these problems, you can think about converting to and from moles in two different ways. If you're going to the left, you can convert from atoms / molecules to moles using what we know as Avogadro's number is equal to 6.02 times 10 to the 23rd objects. So you can use this conversion factor to convert from atoms to moles and moles to atoms. Now on the other side of this flowchart, on the other side of moles, we have mass in grams. And this also has its own conversion factor. This conversion factor is referred to as molar mass. So here I've labeled molar mass over here, and 1 mole is equal to X grams of a substance. And the reason I use X here is because that number changes depending on the substance. If you have an atom, then you just choose the mass of the atom off the periodic table. But if you have a molecule, you add up the atoms of that molecule and figure out its molar mass like that. So this is the conversion factor to convert from moles to mass and mass to moles. Now ultimately, you would expect that I could set up a problem where I give you atoms of a substance and ask you to calculate the mass, where I ask you to go through 2 different calculations. The first one using Avogadro's number to convert to moles, then using the molar mass of that substance to convert to grams. Or I could give you mass and convert to moles and then to molecules. I'll say, for example, how many atoms are in 25.0 grams of water? And so I start with the 25.0 grams of H2O on top over 1, and I convert from grams of H2O to moles of H2O using this conversion here. I have mass and I'm converting 2 moles. I'm going to use the molar mass. Now I listed for you the molar mass in this problem as 18.02 grams per mole. That is how many grams there are in 1 mole of water. Now I could hit equals here, but I don't necessarily want to hit equals here. I'm going to actually take this and multiply by another conversion factor, which converts from moles to molecules. So I'm going to put moles of H2O on the bottom. I'm going to put molecules of H2O on top, and I'm going to use Avogadro's number, which says there are 6.02 times 10 to the 23rd molecules of H2O in 1 mole. And I'm going to put this into my calculator and hit enter. I'm going to take 25 divided by 18.02 and take that answer multiplied by Avogadro's number. And my answer turns out to be 8.35 times 10 to the 23rd molecules. Your calculator probably says 8.35 E23, but remember that's not proper scientific notation, so you need to calculate that number and translate it out into proper scientific notation like this. Well, that's the end of this video lesson. These are all applications involving molar mass. Thank you for listening.